Okay, good morning, everyone. Thanks for dropping in. Let's see, we have about 80% of the class or so. Um, okay, so here's what we got. We're still in kind of the review and reset of linear systems, but we'll finish that up today and we'll get into a little review of probability and statistics and how that's going to play into the class. We kind of left off in the midst of an example problem, of which there is one very much like it on the homework. So we will continue with that in a moment. Just to point out, in case you didn't get the message, office hour will be Fridays at 3 o'clock, since that was the best time that could get the most, most students available. I realize it doesn't get everyone. But, we can always set up other times if you need to. And that means, with the homeworks due, technically due on Moodle at 5 o'clock on Friday, that doesn't give you a lot of time. I understand. So as I said, I'm going to leave the times at which things are due on Moodle at 5 o'clock on Fridays. However, if you need to extend into the weekend, that's fine. The submission will not close on Moodle, so you'll still be able to submit after 5 o'clock on Friday. And I'll just say I'd like to have them before Monday morning, because I'm not really going to look at them or grade them over the weekend anyway, right? So that's fair. I'm going to leave it at 5 o'clock on Friday to encourage you to try to get them done, before then, so that you can have a weekend, or at least it won't be my fault that you have to work on the weekend. But if you need extra time, that's going to be okay. Does anybody have any questions at this point? Okay. Then I'm going to pick up from where we left off here. Okay. And so that was this very simple discrete system that basically says if we put a delta function in, we're going to get out basically 3 points of that are decreasing like this. Okay, and so the first thing we looked at, and basically where we left off, was, okay, could we compute the step response of this system? And the answer is sure, because, well, what we know, right? Anything we put in, we just do a convolution with this guy and we can compute the output. But I approached it in a maybe slightly different interpretation, although we still ended up doing convolution. And that is that every element that comes into the system is a delta function, right? Since it's a discrete system, it's pretty easy to see that. So the input is a sum of delta functions at different times. Okay, and that would be true of any discrete system. It's just a sum of delta functions at different times. And then each delta function generates an output equal to this thing. And so all we really have to do is consider, every individual delta function, apply that output. The outputs overlap each other. That's going to happen in linear systems. And then just add up all the contributions. Okay. In this case, it was relatively simple because this is a short sequence of 3. And so we could calculate it that way. Now, you can extend, this was a unit step function. So it's 0 up to time 0, and then it's 1 after that. But you could extend this idea to any input function, right? Because then all we have to do, the only difference really would be that we would have to scale each one of these elements by the amplitude of that input delta function. So if this wasn't a unit step, but let's say the first one was scaled to 2 and the second one was scaled to 1/2. Well, we just have to multiply this element by 2 and multiply this one by 1/2, and then continue to add them up. Okay. So again, that's convolution, but from a different perspective. And I kind of prefer to look at it from this perspective, that every element of the input generates its contribution to the output in this way. Okay. Okay. So that's where we left off. Now, the next part of the question is, okay, what's the frequency response of this system? Okay, so that's a term with a reasonably specific meaning. The frequency response is going to be the Fourier transform, and that's what I mean by a Fourier transform, of h of k. Right? The impulse response in the time domain and the frequency response in the frequency domain are Fourier transform pairs. Okay. So that says, okay, if I ask for the frequency response, I need to take the Fourier transform of this thing. Now, some of you, but not all of you, may have seen the Z transform before, which would be the way, a way to do this, but I'm actually going to ask you not to do that, because sometimes people try to use the Z transform. We're going to talk about Z transform later in this course. Some people try to do it, but they generally don't get it right. So unless you are sure of what you're doing with that, I'm going to kind of do an example of this another way, which is pretty much related to Z transform. So put Z transform out of your mind for now. And if you didn't know what it was before, no problem there. Okay. The Fourier transform, we're going to be using some of the properties of the Fourier transform to kind of get here. So if we look at, well, I'm just going to roll back to h of k. So first of all, h of k is a sum of three things. Okay. And the Fourier transform is linear. So we can basically say the Fourier transform of this is going to be the sum of the Fourier transforms of each individual element. So I'm going to kind of start there. Okay, that's the linearity property. That was one of our properties. And so I'm going to say, okay, Fourier transform of hk then is going to be the first element, which, and scalars come out, right, because it's linear. And the first element was a delta of k. And then the second element was 0.3 Fourier transform of a shifted delta function. So that's a delta of k minus 1. And then the last one. Like that. Okay, so there we used linearity. Or superposition, I think it said on our little sheet. Okay, well, so that's good because that breaks it down. Now we have, some simpler Fourier transforms to deal with at this point. Well, the Fourier transform of a delta function, which was also on our sheet, is 1. Okay, so that part is simple. Now, the Fourier transform of a shifted delta function is no longer 1, but if I just jump out of here for a second, and you recall this shifting property. So if we shift something in time, basically we get a e to the minus j omega times, however far we shifted it in time, times its regular unshifted Fourier transform, right? So we are basically just going to apply this shifting property to those shifted delta functions. Okay, and so this one is going to end up being e to the minus j omega. And then by the same argument, the one shifted by 2 becomes e to the minus j 2 omega. Okay, any questions about that? We just applied the shifting property. Well, and that's pretty much the answer. Okay, so for our purposes, h of omega is equal to 0.6 plus 0.3 e to the minus j omega plus 0.1 e to the minus j 2 omega. We can't simplify it any more than that. Okay, we can write it in alternate forms, but basically that's as much as we can do. Okay, so that's the answer to the frequency response. Because remember, that's the complete frequency response. It is complex valued, right? It's got j's in it, and that is a sufficient answer. In general, by the way, in general, when we do have mathematical answers, I ask that you simplify them as much as possible. Because again, that's a general thing you should do in science and mathematics communications, is if you can simplify a complicated thing, that is better for communicating what it is. Okay, so I do ask you to do that. Okay, well, but we can't really get any simpler than that with this particular one. Okay, so the next question we ask.
Dr. Lalish.
Yeah, go ahead.
Yeah, sorry about that. If you were to draw the frequency response, what would be the range of omega?
Okay, a very good question that a lot of, and this is something you kind of have to take my word for at the moment, but we'll explain later why this is. In a discrete system like this, okay, and let me just write this out. In a discrete system, remember we mentioned that in discrete systems, there is a limit to the highest frequency you can represent because of sampling and things that we'll talk about later. So in a discrete system, we can really only have omega between 0 and pi as unique. Okay. So yeah, if you're actually, and usually this is okay, but for at this stage, but like on the homework, when you're working with that discrete system and I ask you to plot the frequency response, you really only need to plot it up to omega equals pi. Okay. Up to 2 pi is okay also. And as I will point out, when we get the FFT in MATLAB and we get something that looks like this, right? What we're really getting in terms of those frequencies are the halfway point, which we said was the highest frequency you could get is actually pi in these units. Okay. So if you go up to 2 pi, you get redundant stuff.
Okay. Yeah, it makes sense. Thank you.
Okay. Good question. Usually people don't notice that. Okay. So the next question was, okay, well, what are the real and imaginary parts of the frequency response? Well, we can get that. Go to a little different color here. We can get that simply by, let me get my pen, there it is, by noting that, e to the minus j omega is just cosine omega minus j sine omega. And similarly, this becomes cosine 2 omega minus j sine 2 omega. And so then we could, essentially pull out the real parts, which are 0.6 cosine omega, cosine 2 omega terms. And the imaginary parts are the ones with j's. And so they would be this sine omega term and that sine 2 omega term. I'm not going to write them out, but hopefully you get the idea there. And besides, the real and imaginary parts are not so informative anyway. So not going to be too concerned about that. Okay, so any questions? Again, okay, we have those, but we really can't simplify them any more than that. Okay, but it's going to have an element of a constant value, an element of a cosine that completes kind of one cycle over this 0 to 2 pi, and then an element of a cosine that completes 2 cycles over this 0 to 2 pi. Okay. All right. And then the last thing we ask for, which is going to be more informative, are especially magnitude, but there's also the phase. Well, the phase, if you want to write it out in terms of an equation, we just have to remember that the phase angle is going to be basically the arctan of the imaginary part over the real part. So you do kind of have to find the imaginary and real parts to write an expression for that. And again, with the tangent there and then cosines over cosines and things like that, that's not going to be a simple expression and not very simplifiable. I'm not going to write it out. But basically that follows from having the real and imaginary parts. Okay, the magnitude is going to be a lot more important to us, so I do want to spend more time on that. Now, stop that. There. Okay. So we could, as noted before, basically say, okay, magnitude squared is the real part squared plus the imaginary part squared. But as I've noted, usually that's not going to be the easiest way to do it. So I'm going to do it instead using the value multiplied by its complex conjugate. Okay, and so we're going to do an example with that, which is generally going to be much easier. Okay, so if we I'm going to roll back to, this was our best form of h of omega, 0.6, 0.3 e to the minus j omega, etc. So let me write that. And then to form its complex conjugate, we're just, the rule is everywhere you see a j, you negate it, okay? So and now it's a little painful, but we're going to have to multiply out all those terms. Okay, so anyway, but just keeping that, and I will say, you won't have to do a lot of this, but you have to do it at least once to appreciate it, I think, and what's going on. So you know, basically if I take the 0.6 and multiply it by these three, I'm going to get 0.36 plus 0.18 e to the j omega plus 0.06 e to the j2 omega. And then I'm going to take this term and multiply it by each of these. But what I'm going to do is try to keep things organized, because I'm going to want e to the j omegas to kind of match up with e to the j omegas, and then 2's to match up with 2's and so forth. So I'm going to, so this one, the first term is going to be 0.18 e to the minus j omega. And you might see that those two are going to combine with each other. And then this with that one. So now the e to the j omega and e to the negative j omega cancel out. So this just becomes a scalar without e to the j omega in it. And so that's a 0.09. So I'm going to put that one over here. And then this term with this term becomes a 0.03 e to the positive j omega, right? We have 2 omega and negative omega. So I'm going to have to write this one here to keep it in the same column. And I'm going to write that one there. Okay, 3 terms left. So this guy multiplying here, that's going to give me 0.06 e to the negative j2 omega, which is going to match up with that guy nicely. This one is going to give me 0.03 e to the negative j omega, which is going to match up with the one on top of it nicely. And then the last one is going to be 0.01, and then the two j omega terms are going to cancel out. And so that one is going to go in this column. Okay. So we had 3 multiplying 3, we should have 9 terms, which we do. And now if we combine like terms, we're going to end up with 0.46 plus 0.21 e to the j omega plus e to the negative j omega for that second part. And then this one is going to be 0.06 e to the j2 omega plus e to the negative j2 omega. Now there's one more thing to do, right? Hopefully you recognize these terms as looking something like the cosine. Okay, and so in the interest of simplifying, that's the simple form of this. Okay, now notice that result is magnitude squared. So if we want the magnitude not squared, we just take the square root of that. And that doesn't really simplify. So that's fine. But this is the most informative form of this. Now notice, you know, if you do all the math correctly, since this is a magnitude squared, it should be an all real quantity. Okay, magnitude should not have an imaginary part in it, because we're essentially taking the imaginary elements out in a sense, or they're part of it, but you know, it's like an absolute value, right? So we should, if we do all the math correctly and form this thing right, we should come up with something that is all real valued. Okay, so that's one of the important reasons for doing this simplification, is to demonstrate, okay, there shouldn't be no j's left in this thing. If you end up with j's, you made a mistake, okay, when you're computing magnitudes or magnitude squared. Okay. Any questions about that? And as I said, I'm not going to ask you to do a lot of this, but we need to do an example so you see where this comes from. Okay. Okay, well, that's all nice. And so we could plot that quantity from 0 to pi or 0 to 2 pi and see what we get. But guess what? MATLAB will do all the work for us. And so in most cases, we're going to let MATLAB do the work for us. So we pop over to MATLAB. So the scripts that I use for examples in MATLAB will generally be found on the website. This one's very simple. I'm embedding this 0.6, 0.3, 0.1 followed by a bunch of zeros as our signal, and I'm going to take the FFT of that and then plot the real imaginary magnitude. So in MATLAB, magnitude of a complex number is given by the absolute value function. Okay. And then the function that computes phase is called angle. And so I'm going to just use all of those. So this is a very simple script. Oops. Stop that. Okay, well, so this is the original 0.6, 0.3, 0.1, and then followed by a bunch of zeros. That's not very interesting. We know that's our input to this process. But we plot out the real parts and the imaginary parts, and hopefully you can see that what we have here is, well, a constant value. That was that kind of 0.6 part. And then a sinusoid that basically completes one cycle over this whole range of 2 pi. And then a much lower magnitude element that completes 2 cycles over the 2 pi. That's what gives us this little bump. So those 3 elements are in there. Okay, the imaginary part, similar, but not exactly. It's got some negative elements to it. Because remember, this was a sine of omega and a sine of 2 omega. So they're both in there. But the thing that's going to be more informative about how a system behaves is going to be the magnitude, mostly, with a little bit about the phase. By the way, here's our phase result, and this is in phase in radians. So, it ranges from not quite negative to positive 0.6 radians. It's not immediately obvious what that means. Okay, so, but basically, remember, those are phase shifts of different frequencies. Different frequencies will be shifted differently. I guess that's one thing you can get out of that, but we won't talk about that a whole lot. The magnitude is going to be most informative. Okay, and so again, hopefully this is the square root of that quantity that we just looked at, but it gives us kind of the same information. It says at the low frequencies, we have a response close to 1, and then it drops off as we go to higher frequencies. Right about here is pi, so that's the highest frequency we can really represent. And so these frequencies are more attenuated than the lower frequencies, and therefore that represents something like a low pass filter. Okay, because it doesn't do much. It doesn't scale the low frequencies very much, but it suppresses the high frequencies. It doesn't take them all the way to 0 though, so it's not a very good low pass filter, we'll say. But that's how we might describe this. So again, don't be fooled by the fact that this goes down and then comes back up, because this is redundant. Okay, or the, again, then we could draw that on the negative frequency side, but basically, because we started with an all real signal, those things have to be symmetric with each other. So, any question? Yeah, go ahead.
Could you show us again where the pi is?
Oh, where pi is?
Yeah.
Yeah, I should have been more careful. I should have made these units more meaningful, which I didn't. Those are just in terms of MATLAB index, because it's a length of 128. The halfway point will be where pi is in this plot. Okay, because this will go from 0 to pi to 2 pi. And in these discrete systems, once you get to 2 pi, the whole thing is going to repeat itself. So if we went beyond 2 pi, and we're going back around the same circle again, right? If you kind of think about it that way. So we generally will, we certainly won't go higher than 2 pi on these. But if you just, again, if you just take a discrete system in MATLAB and take an FFT, I mean, it's automatically taking you up to pi, because that's where the FFT goes. Okay.
Yeah.
But we will actually not really use those units, I will say, as we get into this a little deeper. We'll use more meaningful frequency units anyway. Okay. Okay, any other questions? Okay, so you have an example or two like that on the homework. So anyway, that's an example of the way to approach it. Okay. I mentioned this, I mentioned the Z transform before, and the Z transform would get you the same thing in a slightly, I guess, different way. I'm being a little, I'm taking some liberties by using these properties here, I guess. But you get the right answer. Okay, you just have to recognize that this only goes up to pi or so. Okay. All right. Now, so the reason that the Fourier transform is important here, so I'm going to kind of shift away from that problem a little bit and throw some mathematical terminology at you, which you don't, you don't have to know these things, but I do try to use, correct terminology. The Fourier sinusoids are really important for these linear shift invariant systems. I mean, I think you kind of get that, or else we wouldn't be spending so much time with them. But the point ends up being that they are basis functions for these linear shift invariant systems. So what we mean by a basis function for a system is to say that it's kind of like the fundamental function of the system, in that if you put that function into the system, you get the same function out of the system unchanged, except that it gets scaled. Okay. Now, you can't say that for, just any old function that you might put into any of these systems, and hopefully that's clear, right? I mean, here we put in a unit step into this system, but we didn't get a unit step out. Okay, we got something that was related to, but it was changed by the system. And so that's one of the kind of interesting things about this from a kind of mathematical standpoint, is to say, okay, if I take any complex sinusoidal function and I put it into any linear shift invariant system, I'm going to get a sinusoid of the same frequency out. Okay. The only way the system will change it will be to scale it. Now, in this case, scaling can be complex, which will impact both the magnitude and the phase. I'll show that in a second. But basically, if I put a 1 Hertz sinusoid into a linear shift invariant system, I'm going to get a 1 Hertz sinusoid out. Okay. And then they actually the Fourier sinusoids make what is called a complete orthogonal basis set. And the idea there is that if you have a complete orthogonal basis set, you can take any function and break it down into a weighted sum of the basis functions, which we know about the Fourier transform, right? That's one of the ways we talk about the Fourier transform, is to say, oh, you know what that does? That takes whatever function we have and breaks it down into a sum of sinusoids, weighted sum of sinusoids. Okay. And all of those sinusoids, by the way, are orthogonal to each other, which is actually ends up being important in this. Orthogonal meaning that if you take the dot product of any two of those sinusoids, it's 0. In other words, they don't share any information. The information in each basis function or sinusoid is unique. Okay, and there's no overlap or crosstalk between them, you could say. Okay, that's what makes it a complete set. So another example, by the way, of a complete orthogonal basis set is a kind of, in a discrete system, is a delta function basis, because as we said, any function, any discrete function can be broken down as a sum of individual delta functions at different times. That makes that a basis set also, but it's not a basis set for linear shift invariant systems, because if you put that delta function in, you're not going to get a delta function out generally, unless you have a trivial system. Okay. So the Fourier sinusoids are important. I just wanted to point this out. Okay. So if I have some complex number, which I can represent either in its magnitude phase form or in a real imaginary form. This one's going to be more useful here. And I have a complex sinusoid, which is more or less the same form, it's just a function of omega t now, whereas this is just a scalar phase term. If I multiply those two things together, hopefully it's not too hard to see what's going to happen here. Basically, we're going to get a change of amplitude of the complex sinusoid. And then this term, the phi term, contributes a change of phase to the complex sinusoid. Okay, and so remember, a phase shift just basically moves, essentially moves that sinusoid in time a little bit. Okay, so that's what we mean by, okay, yeah, the Fourier sinusoids go through linear shift invariant systems and they're unchanged except by scaling, except in this case, it's complex scaling. So that may alter the magnitude and it may alter the phase. Okay. Okay. All right, so I more or less said this for all linear shift invariant system, the complex sinusoids are a complete orthogonal basis set. If you do this as input, you'll get the same complex sinusoid as output, say for changes in amplitude and phase. You can say, okay, how can I put an imaginary part of a signal into a system? You can't, but the principle applies if it's just a cosine or a real valued sine function also. And of course, we know that any input and output signal can be represented as a sum of sinusoids. So I think I tried to illustrate this before, right? We can think of what linear shift invariant systems are doing as, okay, I have any signal as input. Well, that signal is the sum of a bunch of sinusoids. My system is linear, so I can break it down that way and say that the sum of that the output of that will be, you know, the system output for each of those individual sinusoids. Well, the sinusoids proceed through the system unchanged except for scaling. So think of the system as essentially breaking this signal into all of its frequencies, scaling each one individually, and then putting them all back together. Okay. And that is a model for what linear shift invariant systems are doing. And that's, you know, by the way, if I kind of roll back up here, that's what frequency response tells us, right? That tells us how each individual frequency is scaled by the system, right? If I want to know, you know, what the system does to a particular frequency, I just plug in that frequency here and it'll tell me. Okay. Now, let me, it's a good time for a 2-minute break. Let's do that. I still haven't brought up my 2-minute timer. Let's see if I can find it. I guess that'll work. All right. All right, so let me just quickly illustrate what I'm going to do here. As we talk about these kind of fundamental Fourier sinusoid basis functions. So what I'm going to do is I'm going to say, okay, well, if I go to my frequency space, we'll call this F frequency. And I essentially take one element of that and turn it on, and then invert the Fourier transform. I'm going to see what that particular basis function is in the time domain. Okay, and that's the function that will proceed unchanged through my system, unchanged except for scaling. Okay, so MATLAB, I have a second script. And again, basically what I'm doing in each of these examples is setting up a vector of zeros, turning one element on and then inverting the FFT and then plotting that result. Okay. All right. We'll get to that one in a second. Okay, I'll make this big. Right. Okay. So this is what frequency equal to 1 looks like. And basically, it's going to come, you'll notice that it's a sinusoid that completes one cycle in the full recording period. Okay. Simple enough. And it completes one full cycle. I think that's important to note. The frequency equal to 5 element, you'll notice goes 1, 2, 3, 4, 5, and completes 5 full cycles of a sinusoid in the recording period. Okay, whatever the recording period happens to be. In this case, it's 128 samples long. We didn't say what the real time associated with that is. Okay. And then we have frequency equal to 39, which doesn't look quite as pretty. I'm not going to count them. You can take my word for it that that completes 39 cycles. They aren't beautiful in the sense that they don't look exactly like sinusoids, but that actually is the frequency equal 39 discrete sinusoid under these conditions. So as far as the discrete system is concerned, that's a sinusoid. Okay. More or less what's happened is that, you know, first of all, we've joined sample points with lines, which isn't totally fair. And it's just hitting them at hitting the sinusoidal parts at different parts of the cycle. Okay. But this is a basis function for this discrete system and would, again, if we put that into a linear shift invariant system, we would get something that looks like that out, but it might be, you know, its amplitude might be affected and it might be time shifted a little bit. Okay. But it completes 39 cycles. Okay. And so if I kind of want to refer back to something a little while ago where we talked about, okay, what kind of units do you get from the discrete Fourier transform? We talked about frequency being in terms of cycles per recording period. And so this is the thing that I want you to, you know, start to connect here, is that in this discrete world, okay, the elements of the Fourier transform space are in terms of cycles per recording period, and those are integers, okay? In other words, that's 1 cycle per recording period. That's 5 cycles per recording period. That's 39 cycles per recording period. And if we know, you know, again, if we said, oh, the recording period is 1 second, then we can convert those to hertz, right? But it depends on what the recording period is. Okay. But that's how we're going to interpret the frequencies from MATLAB. Now, one other really important thing, okay, and I'll remind you of this, but you're just going to have to get used to it. Because MATLAB starts counting vectors and arrays at element 1 instead of element 0, the frequency 1 term actually is element 2 of the array. The frequency 5 term is actually element 6 of the array. Okay, because the first element of the array, element 1, is 0 frequency, right? That's just because MATLAB chose to make everything one-based instead of zero-based, like a lot of other programming languages. Okay. And so that's a thing you have to get used to. So if we have a signal and we take its Fourier transform with the FFT in MATLAB, and we want to interpret what different frequencies are, well, we have to make use of that property. So we always have to subtract 1 first, and then that tells us how many cycles there are per recording period. You know, I'm going to actually see if I can just throw a quick example up on that. Sure, let's see what's in here. Let's see, do I have a time? Yeah, I don't like that one. Well, I'll tell you what, we're going to do an example in a bit. So that'll be a little more effective, I think. Okay. All right. So that's, this is an important point for how we interpret taking Fourier transforms. Okay. Now, this is an example, actually, of a signal. This is actually from the Bruce book, which again, nobody can really get, and it's hard to read anyway. So it has examples and along with MATLAB data that I've provided you already by way of the website. So you can have access to that stuff. In this experiment, somebody measured body temperature for pigeons, and they were in a room that basically had a 12-hour light dark cycle, and they're interested in studying circadian rhythm. Why you want to do this, I don't know, but it's a biomedical signal, so we'll go with it. The recording period here is 48 hours. Okay, so they basically did 12 hours on, 12 hours off, and then repeat. And essentially, you know, these are the things we want to talk. I want to talk about. You know, what is the Fourier transform of this signal going to look like? What information can we get from the Fourier transform? So this is the data. Okay, recording for 48 hours. And so you can look at that and say, okay, well, it does look like it kind of, you know, has some elements of repeating every 24 hours. And lights on, lights off, lights on, lights off. So you see some elements of that circadian rhythm that they're trying to induce here. That's more or less what they're trying to do. And so a way we could study this signal is to say, okay, well, let's fit some sinusoids to that. And so the first thing that they do actually in the Bruce book with this is they take the original data in blue and they find kind of, first of all, they kind of take the average value of it, which would be the zero frequency or DC term. You guys have probably heard that. And then they say, okay, we're going to find the best fit 2-cycle sinusoid to the data, which is the one I've drawn here with the dashed line. And then we're going to subtract off the error between those two things. And then this is what we get. Okay, that's essentially what's left after we fit this with that dashed red sinusoid. And then we can do that again. You could say, oh, 1, 2, 3, 4, 5. There might be about 6 cycles in that one. So let's try fitting a 6-cycle, best fit 6-cycle sinusoid to the remaining error. And then subtract, and you know, then there's some error left after that. But at this stage, then, if we bring together the average value, the 2-cycle sinusoid, and the 6-cycle sinusoid, we have something that, fairly closely approximates the data, the green dashed line there, but it's not perfect, of course. Okay. And so we could, again, subtract off this and find what error is left and try to fit another sinusoid to it. And there's the remaining error. It's a little hard to see a sinusoid in that, I grant you. Okay. But you could continue that process of successively fitting sinusoids to the remaining error, subtracting off, and so forth and so on, and do that kind of iteratively. But that would be a pain, right? And the whole point, another way of looking at what the Fourier transform is doing is it's doing all of that automatically for us and obtaining all of those at the same time. Because what we did here was to find, this is the frequency equals 2 cycles term, 2 cycles per recording period element that we would get in the Fourier transform. And this one is the frequency equals 6 cycles per recording period element that we would get from the Fourier transform. Okay. And by the way, the average value is the frequency equals 0 term. Okay. So basically what we did here was we added in 3 terms of the Fourier transform to approximate this. Now, there's still some stuff left, right? That doesn't represent the whole signal. And so there are elements of other frequencies there. And rather than having to go through this kind of ridiculous iterative process of continually fitting sinusoids to it, Fourier transform does it all for us. So why bother, right? And so, yeah, you would never do this, okay? And I'm not going to ask you to do this, but it's a way of kind of seeing what the Fourier transform is doing for us, and that these frequencies might be meaningful. For example, this is 6 cycles, but the experiment took these birds through tried to impose 24 and 12-hour cycles on them. So the experiment didn't cause this, right? This is 6 cycles over 48 hours, or an 8-hour cycle. The experiment didn't do this. The conclusion is this is a natural rhythm for these birds that's internal, not imposed by the external light-dark cycle. Okay. Again, we don't really care, but that's what's going on. And so we can kind of take that whole idea into MATLAB. Actually, let me clear and then get the circadian data. Okay. Okay, so basically, where are you? You're hiding. There. Okay, so that's the data that I showed you before. Now, if we take the Fourier transform of that, what I'm going to do is take the, we'll do this. Okay, so I'm going to plot the magnitude, that's the ABS function, of the Fourier transform of that data. That's, you know what? I'm going to semi-log y plot that so we can see it, the details a little better. And this is another thing that, you will hear me talk about a lot, is using appropriate scales for your graphs so that they communicate the important stuff. Whoa. I do not know what happened there. Give me back my plot. Okay. So this is the Fourier transform of the temperature data. You'll notice the redundancy above this point, the halfway point. There are, what, 36 points in the data. And, well, hopefully it's clear, but if you have 36 points in the time domain, you take the FFT, you're going to get 36 points in the frequency domain. You can get the same number. Okay. So anything above here is redundant. Notice that, okay, that's the index 1 term, but to interpret that in frequency, we subtract 1. So that's the frequency 0 term. So that is the thing that completes 0 cycles over the recording period, which is the average value or the DC term. Most of the time, we're going to ignore that guy. Okay, because we're interested in what's happening with, the actual sinusoids. Okay. So the next highest element is MATLAB index 3, which is frequency 2, completes 2 cycles over the recording period. The recording period was 48 hours. So that is a 24-hour cycle. Okay. And that was the first one that we did the approximation with. The next one is 6 units, MATLAB index. And the way I'm going to refer to that particular unit is MATLAB index, okay? Because that's basically the index into the array. But that's frequency 6. And so it completes 6 cycles over the 48-hour period. Okay. And you could do, and that's the next one that we approximated with. It's got the next highest content, right? I mean, we knew that, or I knew that, and Bruce knew that when they went into it. But and so on. And so you could look at, the other things and talk about the relative content of those things. But in interpreting that data, right, in real world terms, we have to look at this and say, okay, what is that frequency in real world terms? And in order to do that, we need to know, we got to subtract 1 from the MATLAB index. We got to know that means it completes 2 complete cycles over the length of the recording period, and we got to know what the recording period is. Okay? Any questions on that? All right. So that's how we're going to be able to interpret these MATLAB FFTs in real world units. And that's how hopefully you see, that's how you relate them to the experiment. Also, right? The experiment was done, with these 12-hour on, 12-hour off cycles. And if we want to relate those frequencies we see to those, we really need to be able to interpret them in terms of, hours rather than just indices on the MATLAB array. Okay. Any questions? All right. Okay, just a couple of other little things to mention from linear systems, describing different types of system responses, right? Low pass system or low pass filter, basically, if I'm going to illustrate these, is one whose frequency response, oops, is going to look something like that, right? Basically, it allows low frequencies to pass. Sorry. It allows low frequencies to pass, but suppresses high frequencies. The opposite of that is the high pass system, which would look something like this, right? It suppresses low frequencies, but allows high frequencies to pass. Okay. And we can also talk about bandpass systems or bandpass filters, which basically give us a band of frequencies that pass. And then the opposite of that is a notch, or I'll say or band stop. Usually notch implies a relatively narrow one of these, but basically it's a system that does something like that. Okay, passes all frequencies except a certain band. And so this is a kind of shorthand way of describing, you know, how some systems behave kind of basically. Okay. Any questions on those? Those hopefully are familiar terms. Okay. Okay. Last thing about linear systems is the idea of a cascaded system. Okay. And this is helpful, you know, in general in system analysis. So a kind of fundamental thing in engineering, especially engineering of systems, is to take a complex system and break it down into elements so that we can look at individual elements and then be able to also combine them into the larger system. And so what we know, you know, again, based on linear, if these are all linear shift invariant systems, if I have one system or subsystem followed by another, in this case, okay, the frequency response of the complete system is the products of their individual frequency responses, right? And so this is a place where, yeah, okay, we could talk about their individual impulse responses in the time domain and convolve them all together, but it would be a pain to do all those convolutions, right? And so it's much easier to think of these things in the frequency domain anyway, because the net impact of the system will be the product of their individual frequency responses. So let's say we had 3 systems and they're all low pass systems. And they're, well, I'll tell you what. Yeah, okay, let me be consistent. You know, I alternately use F and omega for frequencies. So I hope that's not confusing. We'll call these omegas since that's what's on there. Okay, so the frequency responses of each of these, and we'll say this is magnitude H1, this is magnitude H2, this is magnitude H3. Let's say, stop that. H1 has a response that looks like that. H2 has a response that looks like that, and these are all roughly on the same scale. And H3 has a response that looks like that. Of those 3, which one governs the properties of this system? I should have made it a poll. I see a 2. Or at least you're asking for peace, Alex.
Oh. Yeah.
Okay. Yeah, it's number 2, right? That's the bottleneck, because if we take the product of these things frequency by frequency, right? Even though this guy passes higher frequencies, this one doesn't, and they're all going to get held up by H2. Okay. Also notice that it doesn't matter what order these happen to be in, if everything's linear, shift, invariant. Okay, you're still going to get the same result. But yeah, H2 is the bottleneck. And so, one principle that comes out of this is that, okay, if I have a system and I'm trying to improve its performance, it doesn't do me any good to improve the performance of H3, subsystem 3 in this thing, because subsystem 2 is the bottleneck, right? The net result isn't going to change a whole lot if I make H3 better. So what would be more effective is for me to spend my time working on improving system 2 rather than system 3 or system 1, right? Okay. Any questions on that? Again, should be kind of an intuitive result, but it's something to think about a little bit. Okay. Well, that's basically what we just did, right? Okay. Well, we are almost to the end of our time and only just at the beginning of the probability stuff. So I will, I'm just going to give you a quick idea of where we're going with this, okay? So we are going, the reason we study probability is so that we can apply it to signals that are random in nature. I've kind of already mentioned that, but the most important signal that's random in nature is noise and how we deal with noise. And, a lot of what you do in signal processing is trying to deal with noise, in fact. And so we will spend a fair amount of time with that. But the important thing to get out of, all this stuff where we're going is that dealing with randomness is something we do kind of, we try to optimize it, our performance on average, right? In other words, there are going to be random fluctuations, and sometimes, maybe we're going to do better than average, and sometimes we're going to do worse than average. But what's important over the long run is how we perform on average, okay? And trying to kind of optimize things for that. So with that idea, we're going to have to talk about random variables, probability density functions, and what's going to end up being most important, which is probably, again, in your probability and statistics course, you did talk about this, but it might not be foremost in your mind. And of course, in the BME program now, we don't require probability and statistics anymore. But, we'll get there and try to reinforce this idea, is the fact that of describing the relationships between two things that are random but related. In other words, their randomness is related, or they're dependent on each other, because we're going to find that that's how we describe random signals, through their kind of dependency over time. And that's a foreshadowing, which is about as far as I think I'm going to go today. Okay. So, okay. Any questions at this point? We all good? Okay, so office hour tomorrow at 3. You can also, some people like to send, when they're working on homework and they have a question, some people like to send questions by email, and I try to get to those as soon as I can, and that's fine. So lots of opportunities. Okay. All right. Thanks, everybody. I'll stay on till everybody's off if there are any other lingering questions, but I'll cut off the recording now.